mathematical constructs that we are going to use. One of them is a gradient, one is the divergence, and the last one is the curve. All of these three mathematical constructs, all of these three operators, they are in principle, they are derivatives, okay? Because they all use this operator, divergence. It is the divergence with any vector A, and the curl would be the curl with any vector A again. Okay. So in case the vector A, it's any value which goes like this: 3i minus 2j plus k. So we can immediately ask the following question: what is the divergence of vector A? Can I have an answer from you? So what could be the divergence of A?
Zero.
That's correct. The divergence of A, it is going to be 0 because A itself is a constant vector. Okay. But in case we have a vector B, where B it is a variable such as 3xi plus 2yj plus zk, then we cannot immediately say that the divergence of B is 0 or not. But in this case, we can easily say that this is different from 0. Okay. But if you have any vector C, which can be written as 3yi plus 2zj plus 2xk, what is the divergence of C? What can we say here? So we know that the divergence, it is the rate of change of the first parameter with respect to x plus the rate of change of the second coordinate with respect to y and of the third coordinate with respect to z. So in this case, what could you say?
Zero.
That is 0. That is correct, because the divergence, this would be equal to d over dx of 3y plus d over dy of 2z plus d over dz of 2x. So all of these, we notice that this would be 0, 0, 0. So even for vectors that are changing as a function of space, of x, y, and z, we still could have what's the name? A 0 divergence. Now, let's see a couple of examples. So we initially discussed about the divergence of scalar fields, but sorry, the gradient of scalar fields, and the gradient. This is defined as this defines the maximum change at any point. Okay, or this point is the point of the maximum rate of change, which means the following. This is equivalent to having you are in a mountain and you have a ball and you drop it. If you drop it, you see that the ball is going to follow the path where the slope is the highest. Okay, so this is the maximum change at any point. Let's assume for a moment that we have a change in the electric field. Okay, how can we think of it? Let's assume we have a charge plus Q, and the electric field lines, they have a gradient in this direction. Okay, we know from so far that electric field, this is equal to kq over r squared. Okay, that's it. And then if we aim to find, or we can say the following. So the maximum change at any point, it is along AR. Okay, this is the direction of the maximum change. Or similarly, we can even look at the kq over r. This one has also maximum change along this direction, but then we may be interested into obtaining the gradient of some quantity along any direction, okay? So we may be sitting at this point right here, or we may be sitting at this point right here, okay? Now, the maximum rate of change in this direction is here. The maximum rate of change in this direction it is right here. Let's say that we want to find the rate of change of a vector along a direction dl, okay? Then the rate of change along a vector dl is going to be equal to the gradient of the function dot product dl. Okay, so this will be the rate of change along this specific direction. And mathematically speaking, we can define this one. This can be written as, well, I think we almost mentioned this. This is the gradient of f dot product al. Because dl, it is infinitesimally small order, and an example that we can ask here is the following. If this is the maximum direction of the change of electric field or the vector field, how much change do we observe along this direction here? Now, if this is the maximum change, we have to multiply with the cosine of this angle. So the rate of change along this path is going to be equal to 0. Because let's think about this one like this. The potential V at this point is equal to the potential at this point. Okay? And then if you want to find the gradient between any of these 2 points, it would be 0. Okay, so similarly, also it is 0, which means that along the tangent line of the direction where the change is maximum, here we observe 0 change, let's say. Okay, so in this case, if we have here dl2, then we can simply report that along this direction, the delta V is equal to 0 along dl2. Let's assign here a dl1. We can say that delta V is equal to maximum along dl1. Okay. We're going to see examples, but this was just to remind us also not only on the mathematical aspect, but also on the what we understand from it. ER cosine theta. Okay. So this was the gradient, and the gradient. It's an operator that actually I strongly suggest if you go at our textbook, you might look at the cover page. You can find all the definitions for all the Cartesian, spherical, and cylindrical coordinate system. You can find the definition of the gradients operators of this one. Okay. Now for the Cartesian coordinate, this is going to be the gradient of V. This is AX, I believe you can see this part, AX dV over dx plus AY dV over dy plus AZ dV over AZ. And then for the cylindrical coordinate system, the divergence, this is going to be equal to AR, and by the way, the gradient for all 3 coordinate systems, it should be related because we know that Cartesian, it is x, y, z. Cylindrical, it is, I believe you can see this part, r, phi, z. And the spherical is r, theta, phi. Now, whenever we find the gradient or anything, we should always include here d over dx, d over dy, and d over dz. Here we have d over dr, d over d phi, and d over dz. So it is expected that you include these three derivatives whenever we define the gradient operator. But one thing we have to be careful, that we have mentioned a couple of times so far, is that whenever we take the derivative of a certain quantity, the unit of this linear operator, it is 1 over meters. So here we are going to have dv over dr plus, what is the next direction for cylindrical coordinate system? It is phi. This is a phi, and here we're going to include dv over d phi. dv over d phi plus az dv over dz. But now, here it is easy for us to notice that here we have 1 over meters. This is 1 over meters. This is 1 over radians. For this, we have to include this metric parameter r. Okay. So on this case, this is correct. And if you remember, last time we mentioned that for x, y, z, we have metric parameters 1, 1, 1. For cylindrical coordinate system, we have 1 r 1. And for the spherical coordinate system, we have here 1 r and r sine theta. Okay, so these were the metrics. And as a reminder, we have that the d volume in this coordinate system, it was simply said like dx, dy, dz. In fact, this would be dx times 1. Maybe it's best if we write it like this. Dx times 1, dy times 1, dz times 1. So nothing has changed. But now in cylindrical coordinate system, this has to be dr times 1 times d phi times r, and dz times 1, okay? Then the d volume in the spherical coordinate system, this should be, let's write this first, 1 times dr, and then we have r times d theta, and then we have r sine theta times d phi. Okay, so these are the metric parameters that we have to include. In the same way, they also appear in here. And now, regarding this is the Cartesian, this is the cylindrical, and for the spherical coordinate system, we have the following: the divergence of V in these coordinates is going to be equal to AR dV over dr plus A theta 1 over r dV over d theta plus A phi dV over d phi. So this is the divergence for the spherical coordinate system. Now, we should write also another triplet of equations for the divergence operator. And the divergence, we're talking about this one here, and the divergence for Cartesian coordinate system. This is going to be d over dx, dax over dx, plus d ay over dy plus daz over dz. The divergence in the cylindrical coordinate system is going to be equal to This is equal to 1 over r dr over r rar plus 1 over r dA5 over d5 plus az, derivative of az with respect to z. Now, the best thing is if you can follow me from the textbook, you can read this from the relevant pages from the book, and you can even correct me. And now textbook, you know that it is David Chen. And now, similarly, we have to write also the divergence operator for the spherical coordinate system. And in this case, we will have here 1 over r squared d over dr times r squared ar plus 1 over sine theta d over d theta a theta sine theta plus 1 over, wait a second, r sine theta sine theta dA5 d5. Okay, so this is the divergence in spherical coordinate system. Now we can have a look at a couple of examples. So let's assume we have a potential, or let's say that we have a vector A, which is equal to AR, okay. So that's a vector in a spherical coordinate system. The question is, let's find the divergence of A. You can see this part, okay. So, and then we know that any vector, we can write it like this. A, it can be written as ax plus ay plus az. Okay, so any vector can be projected through some values onto orthogonal directions. Similarly, this can be written as ar plus A5, sorry, it's not A5, let's assume we are doing this in the spherical coordinate system. The second one should be theta, okay, so we are doing this spherical. This is A theta plus A5, where the little vectors here, they denote the direction of the unit vectors along these three coordinates. And now, in this case, what we need to do is that we have to carefully identify what is, here we have to identify what is AR, what is A theta, and what is A5. For this example, we see that the AR, it is simply R, A theta, it is 0, and A5, it is 0. So all we need to do here is that we need to include, wait a second, we have to include these three values into these equations, okay, in this one, so because this is the divergence. So then let's continue here, let's try to write the same expression as in here. This is 1 over r squared times the derivative with respect to r of r squared times ar. This is r squared. So what is ar? The projection of this given vector along the ar direction. This is just r. Then we continue here, plus, but in fact, assuming that a theta and a5, they are both equal to 0, most probably these two terms will be equal to 0.
Professor,
yes.
Sorry for interruption, but we can see that part on the top of the table.
you should remind me. Is it better?
Yes,
Is it good now?
almost.
Yes, wait a second. This is way better, I believe. Yeah. Okay, thanks for reminding. So what we are doing here, we're just carefully trying to write down every respective term. So this is plus 1 over sine theta times the derivative with respect to theta of a theta sine theta. Okay, plus 1 over sine theta times d. In fact, here we're going to write this a5 for sure, a5. But what is a theta? A theta here, it is simply a direct zero. Okay, and a5 it is also zero because they are constant. They are 0 times this 0. This is 0. So if this is the case, this whole term 0, the derivative of any 0 with respect to theta, this will be cancelled out. This will also go away, and then we will be left only with 1 over r squared d over dr of what? This is r cubed, and the derivative of r cubed with respect to r. What is it? What is this derivative? What is this derivative here? The derivative of r cubed, it is 3r squared. So at this point, this is simply going to be equal to 3. Okay. This is it. Another example is if we give a vector a, which is equal to, let's see, a second. Or let's do another example. Let's give, is this example clear? So, assuming that the electric field is equal to the negative gradient of the potential, we have to find the E. So, we are given a scalar quantity, which is in spherical coordinate systems. So, then we have to write down, I'm sorry, this is wrong, this is just gradient. This should be not dot point. And at this part, we should consider so those three on top, they are the gradients, and those at the bottom, they are the divergences. So in this case, we have to use this expression for the spherical coordinate system, and then we find that electric field is equal to minus AR, the derivative of V with respect to R. What is the derivative of V, of this potential with respect to R? This is cosine theta plus A theta times 1 over R times the derivative of V with respect to theta. Now, the derivative of V with respect to theta, it is equal to minus R sine theta plus A5 times dV over d5, 1 over r sine theta. What is the derivative of V with respect to phi? this is just 0 because phi does not explicitly appear in this expression. So this will be cancelled out, and then the electric field will be equal to minus AR cosine theta plus or minus A theta sine theta. Okay, so this is the electric field for this potential given by this expression. So it is strange that the potential can be proportional to R, which would mean that increasing the radius, the potential is increasing. Often, if we have a point charge, the symmetry could be slightly different, of course, because we are used to this expression where potential is kq over r, where r will be a distance, but probably the given parameters could be different, or we don't care how this is created, but it is not very intuitive, because when r goes to infinity, that means that we could have a potential which diverges to infinity also. Okay, so we talked about we said that we have the divergence, we have the curls, and we wrote a sine theta. Wait a second. Okay. In the previous session, we defined or we talked about a vector, which we consider this one the position vector. Now, what could be the most generalized expression for a position vector? A position vector is anything which can be described like this: x, y, z. Okay, this is a position vector. And now, if we express for it is any point which can be generalized in this way. Now, in a vector form, this means that we can write this x, ax, plus y, ay, plus z, az. Which means that it is z along the z direction. So how can we do this? This can be 3, 2, 1. What does this correspond to? This corresponds to 3 units along the x, that's how we do it. 2 units along the y, and 1 unit along the z. Okay. Anyway, so this is 1, this was 2, and this was 3. So now this is the position vector, and we may be interested into, so this is, wait a second, we may be interested into obtaining the gradient of this R. which would be the following. The gradient of R. But R, we have to find what is R itself. Okay, so this is the R, and that means that we have to find a gradient so we have to read that expression. Let's write it here. The gradient of R will be equal to AX dr over AX plus AY dr over dy plus AZ dr over dz. And in this case, we can look for what is the derivative of R with respect to dx. What is the derivative of this one with respect to dx? This is 2x over 2x squared plus y squared plus z squared. Because we know the derivative of any x to the power k is equal to k times x to the power k minus 1. In this case, k is equal to 1 over 2, right? So if k is equal to 1 over 2, then the derivative, we should get these terms. So this is just the first derivative. And this means that here we will get ax so this would be the gradient of this magnitude or of this scalar quantity. And what we observe from here is that we are going to get, we put the common denominator, and this is x squared plus y squared plus z squared, x ax plus y ay plus z az. Now, what we used for this, we used this expression, which is scalar. And then we apply the gradient operator to obtain a vector quantity. And here we have the vector quantity. But as a result, we observe that we have the vector r divided by the magnitude of r. So what this is simply a unit vector, or a vector with length equal to 1 along the direction of this vector. Okay. So, and as a reminder, we can use this part of the board. I just want to remind everyone that for any vector A, which is 3i plus 2j minus k, the magnitude of A is equal to 3 squared plus 2 squared plus minus 1 squared, and the unit vector u along the vector A, it should be equal to 3i plus 2j minus k divided by the square root of plus minus 1 squared. Okay, so this is a similar result with whatever we have here. Now, what this means that for the position vector, and what is a position vector? As we said, there are 3 random coordinates of x, y, and z, which can be like any number here, which were like, say to 1, that's what we pick randomly. And what was the meaning of the gradient? The meaning of the gradient, it was that it provides for us the direction over which the vector increases the most. or the quantity increases the most. So in this case, if we are at any point here, what is the gradient at this point? Well, it's on the point right here. If we are at some point here, what is the direction? So we can ask the same question in two different ways. The first version is this. What is the direction over which the quantity increases the most? Here it is. The second version of the question is, what is the gradient? It's the same thing. So we can say this maximum increase. This is equal to this gradient. And it is imperative, it is easy to figure out that if we are at any point like here, we can, and we're given the distance like this, or the distance like this, that if we count backwards, what will happen? We're going to decrease x, y, and z. That means that this is, we're decreasing them. Or we can just count in a direction tangent. That means that we are not increasing one, in this case, these values enough. So this would not be the, let's say, and actually, if we move in a direction tangent to this unit vector r, then the change would be equal to 0, because we would preserve the radius being a constant. So imagine you are walking over the surface, outer surface area of the planet Earth, and any point on the planet Earth it has coordinates x, y, z, and you are just moving tangent to the perpendicular direction, the gradient or the change over the surface of the Earth would be equal to this. Okay? So this was the gradient. We can give a short break, but I want you over a short time to have a look, try to identify the divergence of these vectors. A equal to, let's write it like this, A equal to AZ and B equal to Z AZ. Can you find the divergence of A and the divergence of B? Okay, let's give a short break.